I'm starting the recording.
Okay.
Yeah, Shaju. So, can you please tell us about yourself? Introduce yourself.
Yes, sir. Myself, G. Kennedy Shah Singh from Tamil Nadu. Sir, I did my BE in the stream of mechanical engineering and I passed out in 2019. After that, I get a chance to work as a apprentice trainee in Navy Lignite Corporation. Currently, I am working in BARC Electronics Limited as a trainee engineer. Currently, I got selected for I cleared the written exam of BARC TOC. And I am going to appear for that BARC TOC interview. Sir.
Yeah, great. So, where are you working right now?
BARC Electronics, sir.
Bharat Electronics. Okay, so
Mm.
we are already at a PSU, and why do you want to switch?
It's a temporary post only, sir.
Okay, it's a temporary. Yeah, so maybe 2 year, 3 year. I think usually
Contact
3 year
basis.
one. Yes, and
Yeah,
they
sir.
get some
3 years.
extension. Yeah, so actually, it's nice thing. You have you already have experience of a government
Yes, sir.
organization. That's cool, actually. Yeah. So, why do you want to join BRC?
Sir, BRC, sir, actually, I have some interest on research side. Because day to day, I will, if I join BRC, day to day, I will explore new things. If in current job, I was doing the same job daily. So currently, I'm in material management. I will go to office. I will do the same job. Tomorrow also, I will come to office. Tomorrow also, I will do the same job. After certain times, it will be that. Ability of knowledge will be easily get the saturation limit. But once I get into the bark, I hope I will learn for my lifetime.
Definitely. So, what are subjects you are comfortable with, you think you have a good grasp on?
Sir, fluid mechanics, thermodynamics, and HM, heat transfer. Sir.
Okay, so essentially I can see you not touching the design side at all, huh?
Yes, sir. Up to now, I am not in that much confident. I am going to that. Sir.
Okay, you're going through that. And do you think, just using the thermal side, one could be a good mechanical engineer?
Mm, No, sir. Actually, no. But I am studying SOM, but up to now, I am not that much confident to take that.
Okay, so given you are studying, let's start with SOM then, okay? How does that sound?
Mm, Okay, sir. What?
Okay, okay, yeah. So, we have a stress strain curve.
Yes, sir.
And do you know what is universal testing machine?
Yes, sir. I will know.
Great. So
Testing
what
machine.
does a universal UTM does exactly?
Sir, the universal, what they will get means the ultimate tensor strength you can find from that. Sir. In what point that exactly when the mile shield will broken, for which load it will broken, then that we can calculate the ultimate strength of the material.
Correct. And is that the only thing that a universal testing machine provide? Ultimate tensile
Mm,
strength?
No, sir. It can provide some other details also because once you fix the item in the that, once you are applying the load gradually, then
Right.
it will show you also at which point it starts deformation also.
Correct.
At which point it got deformation, at which point it got broken. So from that you can get okay, our material have this much plastic deformation zone. That also we can get, sir.
Right. So the UTM essentially generates a curve, a graph.
Yes, sir.
Yeah. Which what
Yes, sir.
what curve is it?
It's less sustain curve, sir.
Stress strain curve. Okay.
Yes,
I'll
sir.
give you one more chance. Does it generate stress strain curve?
Sir, actually, we can obtain sustain curve, but what it will give means that load stress deflection curve, I think.
Correct. Correct. So it essentially gives you load versus deformation. And how would you convert it into stress strain curve?
So by using that numerical formula, that load by deflection that area, at different loads we have that area of that material. Different load the area will be changed. We can change that to stress. From stress we can from the rate of deformation we can calculate the strains.
Correct. Correct. Uh, so let's say you have two specimen. One has a lower temperature, one has higher temperature.
Okay.
And if I put both of them in UTM, what will be the exact difference that you see? It's the same metal, let's say iron or an aluminum, something like that. And one has higher temperature overall.
I think, sir, that higher temperature one will deform little faster than the lower temperature one.
And why does that happen?
Yes, Because the once you are heated the material means the intermolecular forces are a little bit free to expand material in solid. It can free to expand though once you apply the load it will easily come out. But in that low temperature material is not that type. It will come. It will take some extra time that the high temperature material. I think.
Yes, that is this is actually correct. So, do you know what is torsion?
Yes, sir.
Yeah, can you explain a little?
Uh, torsion is a type of load you can apply in that circumference of the material. Sir, with the torsion you can twist the material.
Correct,
You can fix one material that you can twist by applying the torsion on it in one end.
correct. So, not exactly related to torsion, but I'll ask you a question. So, in industry, anywhere actually, whenever we want to pick up some load, you will always see some wires. How are they exactly? Can you describe those wires to me? Let's say you have a crane, and do you use flexible wires in a crane, or a very what
Yes, sir.
kind
I
of?
think.
Hmm?
Sir, actually, it depends upon that application where we are using that.
Correct.
Suppose if I have using that to pick only picking means I can use that belt or some type of belt because that's around some good strength in tensile. Because for some compressive material I can't use belt. So
Obviously,
depends
obviously.
upon the material. I will choose that, sir.
Correct, correct. And those type of wires are also used in bridges and those kind of things.
Mm.
So my question
Yes,
is,
sir.
those are essentially twisted. Have you ever seen those?
Yes,
Yeah, why are they
yes, sir.
twisted?
Yes, sir, because they are twisted to increase their strength, sir. Because once you are it is twisted means it is all are connected in the series pattern. Just so it can pick you a more load for that.
Okay, that although that's correct, but that's just half correct. That's just one of the purpose of twisting them. The another one is even more important and like that. Chalo, let's see. So I'll now jump to fluid mechanics. What is viscosity?
The viscosity is a resistance force. It is applied by one layer from to the another layer, sir, while moving.
Correct. And can you give me some example where viscosity is of use to us?
Yes, sir. Some place viscosity are used to us. I will take a minute, sir.
Yeah, please.
Yes, sir. I will got it. Sir, once you are going to, if we are cutting some material in lathe or something, at that time viscosity is very much important to us. If at that time I have to pour the material which has high viscosity because it has to take the heat away from that material heating zone. At that time, if I am pouring the viscosity having low density, means it will not take that material that much.
Okay, that's example, but we are really not much concerned about taking away material when we machine. It's actually more on the cooling side. Okay, we are
Yes, sir.
having, yeah, more on the cooling side. And although viscosity and density are usually related, but they don't have a very specific relation. Okay, and okay, so that's a good question actually. So let's say you want to cool something. Okay,
Okay, sir.
and you have to choose a fluid for that. So
Okay,
what
sir.
are the properties that you want the fluid to have so that it could, cool whatever you want to cool faster?
First, I will take the material with high viscosity, sir. So it
Why
can easily
viscosity?
flow because it is easily flow to the material, sir.
Yeah, so you want
It
high
is a high
viscosity or low viscosity?
low viscosity material.
Good.
So
And
it can easily go through the material, and
okay, fine.
I hope that
Yeah, forget viscosity. I want a better cooling effect.
better cooling effect means you can consider it has high thermal connectivity, sir.
Correct.
It has
And
high thermal connectivity.
right, right. Good one.
Uh, I am not getting anything, sir, now.
Okay. There is a term in heat transfer, alpha. What is alpha in heat transfer? I don't expect a very concrete answer, but still.
Sorry, sir, I don't have any idea.
Okay, have you heard of thermal diffusivity?
Yes, sir.
What is
Thermal
thermal
diffusion. I got.
diffusivity?
The thermal diffusivity means it is Rosie, it is literally by the is a ratio of heat resistance conductivity divided by that conductive resistance. It's a ratio of convection resistance to conductive resistance.
Okay, fine. And what does exactly thermal diffusivity signifies? Let's say you have two material or two fluid, one has higher alpha, one has lower alpha. What does it signifies?
Uh, Sir, what is here distinguish means if you have higher alpha means you can store less amount of energy into it. If because that rho c means the capacity of energy you are able to store now, sir. Because if you have high alpha value thermal diffusivity, you can storage less amount of energy. So if you have low alpha value means you can store high value of energy into it, heat
Correct. So it will,
capacity value.
cool faster. It will be able to, retain higher
Hmm.
heat. So, like now maybe you can answer what kind of lubricant or what kind of lubricant, not lubricant, cooling fluid will you, need.
Yes, sir. I have to need that as the thermal diffusivity value with low value, low
Correct,
thermal
correct,
diffusivity.
correct. Obviously, there could be other constraint, but yeah, we were more focused here right now. Yeah. Uh,
That was it.
yeah, great. So, how exactly radiation work?
So radiation works means if there is a temperature difference, the radiation will always happen, sir. Whether it will be the presence of medium or it will not the presence of medium, radiation will always there. Maybe the level of radiation will be decide the temperature difference.
You said temperature difference. Does radiation need temperature difference?
Mm. Sir, actually, radiation does not create any temperature difference. If there is a material, it is greater than 0 degree 0 Kelvin, it always emits radiation.
Yeah, correct, correct. To receive it, you need, temperature for, the
You need
opposite.
temperature.
Correct, correct. Yeah. Now that is correct. And what is the mode of heat transfer in radiation?
Um, Actually, radiation itself is a mode of heat transfer.
Yeah, it is made of. What's it based on? I'm asking.
It's based on transfer of waves there.
Yeah, what are the waves exactly? What is the name, if you know?
Mm, that I think electro
Correct, correct. You are right.
sorry, electromagnetic wave.
Correct, electromagnetic waves. So let's say, here is a problem to you. Maybe, both of you can solve it. Okay, so let's do it at the end actually. Okay, it's a good
Okay, sir.
problem actually. So we'll do at the end. Yeah. Anyway,
Okay.
so yeah, you still didn't give me a good example where we use viscosity.
Okay, sir. I will take it. Meet. I will give you a good example.
Okay, you can maybe do it on later time. Okay,
Mm.
that's all right.
Okay,
I
sir.
I don't mind. Yeah. So let's imagine you want to design a ship.
Okay, sir.
Okay, and what are the things that you would try to allocate in terms of we are talking here buoyancy. Okay.
Okay, sir. Because while she's come to design of ship, I will first concentrate about the meta center, sir.
Mm-hmm.
I
Correct.
have to, I have, I have to take all how much all the heavy material as much as bottom. Generally, then only the ship will go up, go down. The meta center will be at a particular time, particular place. I can maintain some good stability, sir. So whatever the heavy items I am able to some engines or everything, I will have to make that in that V shape. Then only it will occupy the more space. Then my center of gravity, so that will come the below that. I place all the in the above, that is mass center will be in above center. So once place it in the bottom, it will automatically come that in the downside. Then that will be the great metacentric height I will get. Then that stability also I will improve that.
Correct, correct. So essentially, we that distance between the geometric center and metacentric center, this that okay, like that. So if I give you a problem, so for example, as you must have heard, everything has some kind of natural frequency. Let's say you are in a
Okay.
ship, and
Okay.
it starts to wobble like this.
Mm.
And if I ask you to find, and it is wobbling because of, the, it's on a fluid. And if we wobble like this, then there is some kind of opposite force. And if I
Okay, sir.
ask you to calculate the natural frequency of that particular wobbling, natural frequency of time period, do you have
Okay,
anything in mind? How would you approach this?
First, I will find that metacentric height.
Okay.
How much will be metacentric? Then I will
Hmm.
directly use that time formula, the oscillation for time 1/2 find root of gm, that metacentric height. Then
Correct.
I will get the time period means. Then I will directly go to the frequency. The frequency means 1 divided by time period. Then
Yeah, yeah, yeah.
automatically I will get the frequency.
You are right. So you know the concept. That was my point actually. So essentially, you can't even have a very high metacentric height either. Okay, not
Yes, sir.
everything can be put at the bottom of the ship.
Hmm.
So you have to manage it somewhere in between.
Okay.
Yeah, great. Uh, yeah. So can you draw vapor compression refrigeration cycle?
Okay, sir. I will
Yeah, draw the TS curve actually.
Okay.
अरे इतना टाइम मत लगाओ.
Yes, sir. I will mark it. Right.
Okay, right. Yeah, that's correct. So what's that, the dotted line that you just made? What do we call it?
So that was eh, that was the expansion process, sir. In the throttling valve. It is something that we say that irreversible things. It is not happen, but we have to make it for our convenience.
Correct. And so why do we need throttling process essentially?
So throttling process means we have to maintain the same enthalpy within that. So once you got that enthalpy will change now, that heat will be it will wasted, sir. So we have to maintain that same enthalpy. So we have to reduce the pressure in a very minute tube. You can
No,
get
no,
that.
I know, like that's great. You know how do we do it, but I am asking why do we do it? Why do we need the throttling process? Okay, leave it. Why do we need the so we are using the compression process here, right?
Yes, sir.
The one on the right in the diagram. Why do we need
Yes,
compression?
Mm, yes, sir. Once you compression, you will it increase the pressure, now, sir. Then that approximate temperature also it will increase.
Correct. So
That
it's
you can
it's
use
it's
it.
not about temperature actually. It's about temperature. Yeah, great. Correct. So you will increase the temperature, and then what? Why are we increasing the temperature?
That we are increasing the temperature. Then in the evaporation we can maintain the same temperature.
Correct. No, why are we
So,
increasing temperature?
why we are increasing the temperature?
What's the process after that compressor process? Compression.
Is the evaporation.
It's evaporation or condensation.
I'm not clear about that.
Okay, so your TS diagram, what's the region on the right side of your TS diagram?
Say it is compression, sir. That isentropic compression.
Correct, correct. No, the TS diagram, you have a bell curve. What is on the right side of the bell curve?
It is saturation vapor curve, sir.
Correct, vapor curve, vapor region. And what is on the left side of the bell curve?
That saturation liquid region.
Liquid curve, correct. Liquid region, we can say, correct. So now, in that particular process that is coming after the compression process,
Mm.
we are going from vapor to liquid or liquid to vapor.
We are going from vapor to liquid, sir.
And so what kind of process is it?
I think it is condensation.
Correct, it is condensation. So essentially, and what are we doing in that process?
So we are taking the temperature, and it will that phase change will happen from that state saturation vapor to saturation liquid, sir.
Correct. Essentially, we are losing some heat, okay, through the
Some heat.
condensation process. And for us to lose the heat, we need to rise the temperature relative to surrounding. Because how else will you lose the heat? Heat will be lost only through one way, that is temperature difference. Okay, you understood it now?
Yes, sir. I
Huh.
understood.
Now can you answer why do we have throttling process?
Yes, sir. After that heat, the temperature loss. After that, I have to again evaporate it. At that time, I have to maintain the same temperature limit for that.
Yeah, you are nearly correct actually. Yeah, that's correct. Yeah. So Shaju, I'll conclude your interview now. What I'll do is now I'll directly start with Karthik, and
Okay, sir.
I'll provide whatever review I have to both of you at the same time. Okay, that works.
Okay, sir. Okay, sir. That
Okay,
that's
okay,
okay,
great.
sir.
Yeah, great. Karthik, can you please come in?
Yes, sir.
Yeah. Oh, hi Karthik. So can you please introduce yourself?
Good evening, sir. My name is Kartik Nath Sharma, and I am from Gorakhpur, Uttar Pradesh. And I have done my intermediate and high school from Gorakhpur only. After that, I have done my BTech from Ajak Margarg Engineering College, and I have passed in 2021 year. After that, I have 1.5 year experience in Tata Consultancy Services. After that, I have resigned and start preparing for PSU. And after clearing that and BARC TO examination, and I am sitting in front of you and giving the interview.
Great. That's great actually. So why do you want to join BRC?
सर मेरा मेन रीजन ये है बार ज्वाइन करने का, क्योंकि ये एक प्रॉपर कोर मैकेनिकल की जॉब है, रिसर्च ओरिएंटेड जॉब है। और जैसा कि मेरे को 1.5 ईयर का ऑलरेडी एक्सपीरियंस है आईटी सेक्टर में, तो जैसा कि मैंने फाइनेंशियली फैमिली को सपोर्ट करने के लिए मैंने मजबूरी में वो जॉब ज्वाइन करा था। और फिर मुझे पता चल गया कि मैं उसके लिए नहीं हूँ। दैट्स वाई मैंने पूरी फोकस इधर ही रखा कि मैं अपने टेक्निकल में ही कुछ अच्छा करूंगा, और रिसर्च फील्ड में जब मन लगेगा तो शायद मैं और अच्छा परफॉर्म कर पाऊँ और कंट्री और ऑर्गेनाइजेशन के लिए और बेटर कर पाऊँ।
Chalo, that's amazing actually. You have a very clear motivation where clear path ahead. So yes, Karthik, what are the subjects you are, have commands on?
सर एट फर्स्ट आई विल कीप सोम, देन thermodynamics, heat transfer, and then fluid mechanics.
Yeah. So I hope you have heard, the interview that went on, just a while ago. So can you give me some example where viscosity is used actually? We need viscosity. I want that kind of example.
सर विस्कोसिटी का मेन जो हम बियरिंग पढ़ते हैं।
Correct.
हाँ,
Okay. Do you
हाइड्रोडायनेमिक्स।
need do you need viscosity in bearing or do you not need viscosity in bearing?
एक्चुअली सर हाइड्रोडायनेमिक में जब हम हाइड्रोस्टैटिक में उतना यूज नहीं कर सकते, क्योंकि उसमें ऑलरेडी हम प्रेशराइज फ्लूइड करके अप कर देते हैं स्टार्टिंग में। लेकिन जब हम बात हाइड्रोडायनेमिक की करते हैं, तो हम चाहते हैं कि ज्यादा से ज्यादा विस्कस फ्लूइड हो। उसकी वजह से हम हायर से हायर लोड को वेरी मतलब कैरी करने में आसानी हो जाता है। क्योंकि
correct.
जितना ज्यादा विस्कोसिटी होगा उतना हैवी हम लोड को बियर कर पाएंगे।
Right, right. So actually, that's a good answer. Although we are more concerned about, the film here. In
यस सर।
yes, so we need a film actually, and the film is generated if it has a higher viscosity kind of thing, because usually viscosity is directly connected with surface tension as well.
यस
So if you have surface tension, then you will have a film, because if you don't have film, there will be direct contact, and
हाँ, डायरेक्ट कॉन्टेक्ट को वियर एंड टियर से होने लगेगा।
करेक्ट करेक्ट, वियर एंड टियर नहीं, बहुत गंदी चीजें हो जाती है फिर, क्योंकि ठीक है
बहुत
ना।
गंदे हो सर, मतलब
हाँ, so
स्टार्ट तो वहीं से।
yes, yes, you are right actually. So at end maybe I'll give you some better example as well. Yeah. So
हाँ,
do you know what cavitation? What is cavitation?
यस सर, कैविटेशन में जब फ्लूइड फ्लो करना शुरू होता है, तो जब वेपर प्रेशर से ड्रॉप हो जाता है फ्लूइड का टेम्परेचर, फ्लूइड का प्रेशर, तो उसकी वजह से एक बैक फ्लो होता है, तो उसकी वजह से अ, जो ब्लेड्स होते हैं वो कोरोड होने लगते हैं।
से ब्लेड करोजन तो बहुत बाद में आया है। व्हाट इज कैविटेशन?
हाँ, कैविटेशन सर अभी मैं बहुत करेक्टली नहीं, बट सर वही है कि सर बबल्स का फॉर्मेशन होने लगता है प्रेशर
करेक्ट
ड्रॉप होने की वजह से।
करेक्ट। एंड व्हाई
तो
डज दैट
उसकी वजह
हैपन?
से सर बैक फ्लो।
यू आर राइट, यू आर राइट।
सर जो, हाँ सर, जो फ्लूइड का प्रेशर है वो उसके जो वेपर प्रेशर से कम हो जाता है, तो वहाँ पे बॉइलिंग स्टार्ट हो जाती है।
करेक्ट
तो
करेक्ट,
उसकी वजह से सर मेन रीजन होता है।
ये दैट्स करेक्ट। कैन यू ड्रॉ रैंकाइन साइकिल?
यस सर, सर सिंपल रन टाइम साइकिल।
हाँ हाँ, सिंपल रैंकाइन, बहुत सिंपल।
सर इसे तो
Yes,
लिख
correct. And quickly explain me the process.
दो। सर एक्चुअली यहाँ पे हम स्टार्ट, सर अगर मैं यहाँ से करना चाहूँ,
Mm-hmm.
तो यहाँ हमारा पंप होता है जिससे हम प्रेशर को इंक्रीज करते हैं लिक्विड फेज में। प्रेशर को इंक्रीज करके फिर यहाँ बॉयलर लगा होता है जिसमें कंबशन होता है। उसके बाद यहाँ हम सुपर हीटेड टेम्परेचर, सुपर हीटेड रीजन तक ले जाते हैं।
Mm-hmm.
उसके हेल्प से हम सर जो भी टरबाइन के ब्लेड होते हैं उसको रोटेट करके फिर से यहाँ पे आइसेंट्रोपिकली इसे ड्रॉप करा के फिर से हम इसको कूल करके फिर से हम इसको ये साइकिल को कंटिन्यू रखते हैं।
Correct. So we have, condenser at the end, right?
यस सर।
Yeah. So why do we have condenser?
सर मेन पर्पस ये है कि पहले जो क्या था कि पहले हम वो करते थे कि जो एक बार फ्लूइड यूज हो गई वो फिर दोबारा यूज नहीं हो पाती थी।
Correct. Got it.
तो
So
हम,
now leave that. Is there any other reason? I agree. We need a cycle. We need to reuse the fluid. Is there anything
यस
else
सर,
that you can think of?
सर उसके अलावा हम एक चीज और कर सकते हैं कि हम फिर इसे किसी भी प्रेशर पे यूज कर सकते हैं फिर इसके बाद से, कि प्रेशर कम करके फ्लूइड कैसा भी हो, फ्लूइड की क्वालिटी को न देखते हुए भी हम इसको फिर से हम कैसा भी फ्लूइड को अच्छे से यूज कर पाते हैं।
Correct. So you are absolutely correct. Okay. Like this is the first time someone answered this. Yes. So that's right actually. So Mm, yes. So, usually the condenser pressure is around, so our atmospheric pressure is 100 kilopascal. Usually condenser pressure is 10 kilopascal.
यस सर।
Can we take it further down?
सर फर्दर डाउन का सर बहुत रफ आइडिया नहीं है, मतलब
Mhm.
बहुत क्लियर आइडिया नहीं है मुझे, बट आई कैन डू द एजुकेशनल गेस इफ यू अलाउ मी।
Yeah, yeah, please, please.
सर अगर हम कंडेंसेशन प्रेशर को और कम कर सकते हैं,
Mhm.
तो पॉसिबिलिटी क्या होगी कि जो वापस से वो मिलेगा हमें एक्सपेंड करने के बाद जो गैसेस मिलेंगी, अगर हम इसे और ड्रॉप करेंगे तो एक्सपेंडेशन के बाद से जो गैसेस होंगी सर
हाँ हाँ,
वो वेट मिलने लगेंगी सर।
करेक्ट। सो टर्बाइन एग्जिट जो है वो वेट हो जाएगा एंड लाइक दैट.
हाँ,
ओके, सो यू
वेट
नाउ
हो
यू
जाएगा सर,
रिमूव.
उससे कोरोजन।
Correct. Now you remove that aspect. Okay, that's not a limitation. You have, diamond turbine here. Okay, there is no corrosion, no erosion, nothing. Can you further it down?
तो फिर सर अगर मैं एटमॉस्फेरिक प्रेशर से फिर ड्रॉप ले जाऊंगा तो उसमें सर इंटरनल जो एटमॉस्फेरिक एयर है वो भी सर अंदर आने लगेगी।
वो तो अभी भी आ रही है, कंडेंसर प्रेशर एट 10 किलो पास्कल.
अच्छा 10 किलो पास्कल, ओके
Yeah,
ओके।
it's already,
तो
much lower actually.
ओके ओके सर।
What is the
तो
limiting factor that, I am not keeping at 1 kilopascal or, even lesser than that? Is there any limiting factor?
सर एक चीज और है कि प्रेशर कम करने से बॉइलिंग की कंडीशन भी आने लगती है, क्योंकि प्रेशर ड्रॉप करेंगे तो वो फिर लिक्विड नहीं रह जा पाएगा, तो बहुत प्रेशर ड्रॉप करेंगे तो फिर जो बॉइलिंग की कंडीशन शुरू हो जाएगी, जैसा कि हम एवापोरेटर में देखते हैं
Yeah,
जब
so
हम वीसीआरएस पढ़ रहे होते हैं तो।
तुमने ये सही बोला है. So I'll give you one more hint. With when we lower the pressure, the temperature of condensation also lowers down.
यस सर।
Now can you try to think?
सर फिर कंडेंसेशन, फिर सर फ्रीजिंग की कंडीशन भी आ सकती है।
अच्छा ठीक है. Yeah, so you have done really well actually. So what happens is essentially you want to lose the heat to the
यस सर।
atmosphere, and for losing the heat to the atmosphere you want the condenser temperature to be
प्रेशर
higher than atmosphere
हायर है
temperature.
देन दैट होता है,
Correct. So essentially I cannot take it further down, lesser than 20 degrees Celsius, 25 degrees
यस
Celsius,
यस।
like that. So that is essentially the limiting factor. So here is a question. When will a steam power plant have higher efficiency, in a winter or in summer?
सर कैन आई थिंक अ बिट।
हाँ हाँ हाँ, सोच लो. लेट्स से मैंने आप कहाँ से हो? गोरखपुर से हो. मैंने गोरखपुर में ये बनाया, पावर प्लांट बनाया. लेट्स से आप इंजीनियर हो एंड आई हैव गिवन यू चांस एक पावर प्लांट गोरखपुर में बनाना है या शिमला में बनाना है. कहाँ पर इफिशिएंट रहेगा पावर प्लांट? गोरखपुर में तो बहुत गर्मी पड़ती है. मैं कानपुर में था, हे भगवान, समर में.
सर फिर दोनों एस्पेक्ट की बात करने लगेंगे कि क्योंकि फिर वहाँ हीट एक्सचेंज, अगर जब गर्म एरिया में यूज करेंगे तो हीट एक्सचेंजर के लिए थोड़ा सा वो होगा
So we
कि
are
दिक्कत होगी फिर।
talking strictly in terms of condenser here. Rest all things are correct. Rest all things are,
ठीक है।
very accurate.
तो सर फिर कंडेंसर के पर्सपेक्टिव से अगर बात करेंगे तो फिर शिमला में ज्यादा बेटर होगा, क्योंकि वहाँ पे
क्यों
हीट
क्यों?
एक्सचेंजर आसानी से।
करेक्ट, क्योंकि वहां पे शिमला का
क्योंकि
टेम्परेचर, एटमॉस्फेरिक टेम्परेचर कम है.
हाँ कम है
तो
तो वहाँ पे सर हीट एक्सचेंज ज्यादा अच्छा हो पाएगा।
करेक्ट, हीट टेम्परेचर ज्यादा अच्छा होगा. हम लोग कंडेंसर के अंदर जो प्रेशर है वो और कम कर सकते हैं.
और कम कर सकते हैं सर।
करेक्ट, राइट. सो yes, correct. That's a good answer. Uh, After that, yeah, can you state second law of thermodynamics?
सर सेकेंड लॉ thermodynamics basically combines with the true statement, Killing statement and Clausius statement.
Correct. So I know both the statement. Now, are these different statements?
नो सर, दोनों एक दूसरे को कंप्लीट करते हैं, बेसिक अगर मैं यही कहना चाहूँ तो दोनों एक दूसरे को कंप्लीट करते हैं, एक दूसरे के पूरक हैं, इसे मैं कह सकता हूँ। एक हीट इंजन के लिए यूज करते हैं, एक एक हम रेफ्रिजरेटर के लिए यूज करते हैं।
Correct. You are right.
तो
Actually,
बेसिकली सर
both of them are essentially same equation, but when have different language, different things used. That is
यस
absolutely
यस
correct. So, can you give me some statement which is in terms of entropy?
सर एंट्रोपी बेसिकली टेल्स अबाउट द रैंडमनेस ऑफ द सिस्टम,
Okay.
कि कोई भी बॉडी कितना रैंडम है। अगर
Mhm.
सर अगर मैं प्रैक्टिकल एग्जांपल।
No, I understand that. Can you state in terms of second law? In terms of
अच्छा
entropy, I want.
एंट्रोपी
एक मिनट,
तो
जस्ट एक मिनट. हाँ, you think about it. Hello. Hello.
यस सर।
हाँ हाँ. Can you state?
Sir, in terms of entropy, we can say that the entropy of the universe is always greater than always be positive, और सिस्टम की एंट्रोपी पॉजिटिव निगेटिव या जीरो कुछ भी हो सकती है, तो
Correct.
इस तरह के टर्म्स
So
में बता
here
सकता हूँ।
actually it's not entropy, it's something else actually. You are right. You're absolutely right.
हाँ,
It is change of entropy actually. We always talk about change of
changing
entropy. Yeah. There
changing
is nothing
entropy.
like
Yes, yes,
absolute entropy. Yes. So yes, that's
that's very
absolutely
right.
right. So delta S of universe or any closed system, as a matter
Delta
of fact,
entropy. Yes, yes.
yeah, it is greater equal to zero. When is it equal to zero? When is it greater than zero? Okay. Shaju, can you तुम भी आ जाओ actually.
Am I audible, sir?
हाँ हाँ अभी
Because
आ रहा हूँ. चलो ठीक है.
actually मेरा
Let it
internet.
be. So here is a question for you actually. So वो रेडिएशन से याद है मुझे. तुम दोनों सॉल्व करो. वैल्यूज थोड़े हाइपोथेटिकल हो सकते हैं. लेट्स से अर्थ पर मुझे पर मीटर स्क्वायर लेट्स से 10 यूनिट ऑफ रेडिएशन मिल रहा है सन से. आई एम गेटिंग
Mm-hmm.
10 यूनिट्स ऑफ रेडिएशन फ्रॉम सन. आई थिंक इट विल बी वैट पर मीटर स्क्वायर. या सो 10 वैट पर मीटर स्क्वायर का रेडिएशन मिल रहा है फ्रॉम सन. एंड सन का जो यहाँ से डिस्टेंस है इट इज 150 मिलियन किलोमीटर.
Mm.
करेक्ट. So based on this info, I want you to calculate what is the temperature of sun's surface.
Okay.
I think this much should be enough. So I have given you, per meter square, 10 watt per meter square
Mm.
of radiation, and I have given you
Mm.
distance of sun to earth.
Okay.
So I don't really want value. Okay, I just want the approach. Can you think of something?
Sir, can you repeat the question?
Okay,
हमें
so
अर्थ पे रेडिएशन इतना मिल रहा
हाँ
है
इतना
तो क्या
मिल रहा
हम
है.
अर्थ
यस 10 watt per meter square and earth distance from sun is, as I said, 150 million kilometer. So what is sun's temperature? Okay, see, meeting is getting over. So what I'll do is we'll have a conference call. Okay, that works.
ओके नो
Okay, I'll give you 5 minutes. Try to